So with these really large numbers or very small numbers shortened into scientific notation, what we could do is carry out calculations in scientific notation form, which makes the work quite a bit simpler so that we're not juggling a bunch of zeros hanging around. What it comes down to is what we saw with our exponent properties. So what we want to keep in mind is with division, we subtract exponents going numerator minus denominator. With multiplication with exponents, we end up adding them together. So let's see how we do this. With this first example, what we're doing is we have scientific notation and we are multiplying. So what we're going to do is we're going to think of these in, I guess, 3 sections. Let's think of this in 3 pieces. We have our values for A. We have, and this is kind of the silly part, but we have our multiplication symbol, and we have our power of 10 piece. So when multiplying together, what we're going to do is think of 4 times 2. So we're going to multiply our numerical piece, our values for A. We are going to have our multiplication symbol. Here we go. And then we're going to have our powers of 10. So we'd have 10 to the 5th power times 10 to the negative 7. So it's just kind of rearranging it, but we're grouping it based on similar pieces that we can combine together. So 4 times 2 is equal to 8. We'll have our multiplication symbol, and then we'll have 10 to the 5 plus a negative 7, which is negative 2. And when we get to the end here, something we want to double check is, does our value for A still work? Because sometimes we may need to adjust it. But in this case, 8 is between 1 and 10, so we're all good to go. Let's take a look at a case with division. Again, I'm going to think in terms of those 3 pieces. So I'm going to have my values for A. I'm going to have my multiplication symbol, and then I'm going to have my powers of 10. So just going to fix that. Okay. So 4 and the negative 1.52, what we're doing is taking 4 divided by negative 1.52. We're going to have our multiplication symbol. And then we're going to have 10 to the 5th divided by 10 to the 9th. Now, for the 4 divided by negative 1.52, we're just going to plug that into a calculator, and that would be a negative 2.63 times 10 to the 5 minus 9, which would be a negative 4. Again, I just want to make sure that that value for A is between 1 and 10, and this is a negative value, that's totally fine, but basically the absolute value, which we haven't talked about a ton, but that 2.63 is between 1 and 10, so we're all good there. All right, division. I'm thinking of 1.2 divided by 9.6 times 10 to the 8th power divided by 10 to the 5th power. 1.2 divided by 9.6 is a 0.125, and we're multiplying that by 10 to the 8 minus 5, which is 3. Now, 0.125 is an issue here because that is not between 1 and 10. So I need to do something to adjust that so that it is between 1 and 10. And something I could do is multiply by 10. If I multiply that by 10, I'm going to get my 1.25. That sounds great. However, I can't just multiply by 10. That changes the value of the number. So what I need to do is make an adjustment that balances things out. So if I'm multiplying by 10, if I also divide by 10, it kind of cancels out, and that I didn't really do anything, but I'm kind of changing the appearance of the number. So if I multiply by 10 over on that left-hand side, what I could do on the right-hand side is divide by 10 so that it's canceling itself out, so I'm not actually changing the value of the number, I'm just changing its appearance. If I divide by 10, then what I'll have is 10 to the 3 minus 1, which is 2. And I just want to check my math real quick. 1.2 divided by 9.6. Yeah, 0.125. Okay. So if we make adjustments, we just need to keep it balanced. And what's going to come through as is either multiplying by 10, which would make us divide by 10 over here, or sometimes over here we might divide by 10, which would make us multiply by 10 over here. But it's all to kind of cancel itself out. So let's see that happen with this case. We're multiplying, so we're going to have 6 times 3 times 10 to the negative 2 plus 8. So this is going to be 18 times 10 to the 6th power. Now 18 is not between 1 and 10, so I need to do is shrink it down by dividing by 10. But if I divide by 10 there, I need to multiply by 10 there so that it cancels out. So 18 divided by 10 is a 1.8 times 10 to the 6 plus 1 is a 7. Okay, 1.26 times 3.21 all times 10 to the 4 plus 5. So carrying out that multiplication, we'll have a 4.04 times 10 to the 4 plus 5 is 9. And we don't need to adjust there because we are between 1 and 10. Okay, we could keep stringing these values together, multiplying, dividing, doing all those things. What this will come down to is we'll have 3.33 times a negative 1.05 times a 5.62. And then our power of 10, we're going to have 4 plus 7 plus 5. So the numerical part should come out to a negative 28.07. Then we'll have times 10, and that should be a power of 16 when we add those all together. Now 28.07 is too big, so I need to divide it down by 10. So I'm getting something between 1 and 10. If we divide by 10 over there, then I need to multiply by 10 on the other side. So this will be a negative 2.807. So now we're good there. 10 to the 16 plus 1, which is 17. Okay, let's look at a word problem here. So we have an average human body contains around that many red blood cells. Each cell measures approximately 0.000008 meters long. Write each number in scientific notation and find the total length if the cells were laid end to end. Write the answer in both scientific and standard notations. Okay, so let's start with the number of red blood cells. So with that, I'd want to express it as 3.0 times, and then I just need to figure out how many spots am I moving my decimal. So we're going to have 3, 6, 9, 12, 13. So that's going to be 10 to the 13th power. Then for the length of red blood cells, we'll have an 8.0 times 10, and I just need to see how I'm moving my decimal. So that's going to be 1, 2, 3, 4, 5, 6 spots. And that'll be in the negative direction. There we go. Okay, so if I want the total length, well, I have the length of each, and then I have the total number of red blood cells. So what I need to do is multiply. I'm going to take the number of red blood cells times the length of each red blood cell. So 3 times 8 is 24, times 10 to the 13 plus a -6, so that'll be a +7. 24 is not scientific notation, so I need to divide by 10 there, multiply by 10 there. So in scientific notation, we're going to have a 2.4 times 10 to the 8th power, which in decimal notation will have 2 and then 1, 2, 3, 4, 5, 6, 7, 8. So the total length is 240 million meters. Those are units there. Okay, so some more examples with scientific notation there and carrying out operations.